All right, friends, welcome to our first video in year-long college algebra. We're going to go ahead and start off with Chapter P, we're calling it. That's P for prerequisites. And this is something that you can find in your textbook. Basically, what we're going to be talking about here are just a couple of basic algebra concepts that you're going to need for future chapters in this course. So we're going to start off where basically every other algebra class starts off with, and that's just talking about straight up families of numbers, okay? And so we're going to go ahead and start off with the most encompassing family, and that's just your real numbers. You guys have heard of your real numbers before, and what a real number is basically any real world number, okay? Any number that you can think of is a real number. We're talking about your counting numbers, we're talking about pi, we're talking about your square root numbers, we're talking about any type of number that you could possibly think of. That is what we would consider to be a real number, okay? It does have the extra note here that says no i's, and what that means is that's referring to complex numbers or imaginary numbers. Those would be basically the only type of number that's not considered to be a real number, okay? The next one here, we're talking about your rational numbers, and hidden inside that word rational is this word right here, which is ratio. And so what a rational number is any number that can be expressed as a ratio, and a different name for the word ratio is basically the word fraction. So any number that can be expressed as a fraction is a rational number. So basically numbers just like 3/4, that's a rational number. Weird ones like 18/13, that's a rational number. But you also have others, right? So you have decimals that can also be considered to be rational numbers because they can be expressed as fractions. So basically any decimal that either stops or repeats, you can write that as a fraction, so therefore it is a rational number. So we're going to have to be on the lookout for that whenever we do that, okay? A couple of other different little families of numbers. There's your integers, so it says a real number that is not a decimal or a fraction, okay? So your complete list of all your integers, I'll just go ahead and write those out here really quick for you. They're basically all of your counting numbers, so like 1, 2, 3, etc. Also, we're going to throw 0 into that family, and then all of your negative counting numbers, so -1, -2, -3, etc. Okay, so it's an infinite list of numbers, and that's the general form of what an integer is. So if we ever say integer in this class, we're talking about a number from this list. What are your whole numbers? Well, your whole numbers are basically part of your body of integers. Your whole numbers are basically all of your positive counting numbers, so 1, 2, 3, so on and so forth. And we're also going to throw 0 in there. Okay, if you are a computer scientist, then the list of numbers that you use to count with are going to be this list of numbers right here, because the first one-digit number actually is 0 on a computer instead of the number 1. Okay, so those are your whole numbers right there, a non-negative integer. And then finally, you got your natural numbers. These are just your positive counting numbers. So your 1, your 2, your 3, your 4, etc., etc. If I were to ask you to count anything, like the number of people in our class, the list of numbers that you would most naturally use is going to just be your counting numbers, 1, 2, 3, 4, and so forth. Okay? So those are just all different families of numbers, and you've talked about these in previous math classes before, but I just wanted to repeat a couple of things here. And then finally, you have your family of irrational numbers. So if we already talked about a rational number being numbers that you could write as a fraction, an irrational number is the opposite of that. So we're talking about a number that you cannot write as a fraction. So a couple of examples of these types of numbers here would simply be, famous numbers like pi. That's approximately equal to, 3.14159, etc., etc., etc. That is a decimal that never stops, and it does not have a repeatable pattern, so that would be considered to be an irrational number. Another example of an irrational would be something like the square root of 2. It has a decimal approximation that is about equal to 1.4141213, etc., etc. So it's a long, ugly, non-repeating decimal. No way to write that as a fraction, so we would consider that to be an irrational number. Okay? So it turns out that any real number that you ever will look at will fall into one of these families, and so one of the questions that I can ask you is I'll just give you a list of numbers, and I'll just ask you to which families they belong. Okay? So we'll just go through these here really quickly. The first thing that we are going to talk about here is this number -e. Okay? And so e, that is actually a number that you may have seen in a previous class like Algebra 2. That is the number that we call the base of the natural logarithm, and it has a decimal expansion of 2.781, blah, blah, blah. It's a big, long, ugly decimal that doesn't have a repeatable pattern, and it never ends, so that we would consider to be an irrational number. So we're just going to go ahead and write that down. Okay, so negative e, that is irrational. How about this next number here? Okay, so we have the number 1/2. All right, well, that is a fraction, so that's going to mean that that is going to be one of our rational numbers. Okay, so 1/2, we're going to go ahead and say that is a rational number because it is a fraction. Okay. Keep in mind, a few of these examples could live in more than one family, okay? So how about that next one? You've got negative 3.14, okay? That is a decimal approximation for the number pi. It's not exactly equal to pi itself, but this is a decimal that stops somewhere. It goes 0.14, and then it doesn't continue. So we said before that this would be an example of a rational number because it would be possible for us to convert negative 3.14 to a fraction. Specifically, you could write that as negative 314 over 100, okay? That would give you in the calculator negative 3.14, so that would be considered to be a rational number, okay? The next one here in the list, it looks like we have 4 times the square root of 2. We just said before that square root of 2 is an irrational number, so that's kind of a dead giveaway that this guy would be irrational here. Again, any number that has a decimal expansion that has no pattern and never ends, that's always an irrational number. And then finally, you've got the very last one here, and that is our old pal, the number pi, okay? And so pi, we've already kind of talked about in the space above. That is also an irrational number, so we'll go ahead and write that down here as well, okay? So these are examples of numbers that only exist in one family, but keep in mind we could have examples that live in more than one family. So for example, if we come back up here to our naturals, our wholes, our integers, is it or is it not true that I could just take each one of these numbers and quickly write over 1, over 1, over 1? On every single one of these, I can do that without any problems because you could do this with any number. You could write over 1 over anything. So that's going to mean, folks, that these 3 sets of families, this integers, whole numbers, and natural numbers, they are themselves examples of rationals because I could just write each of them over 1 and then they instantly become fractions. Okay? So that's going to be something to keep in mind if you're ever asked to classify numbers. Okay? So there's a little bit about classifying numbers. The next little topic that we want to discuss is how to talk about groups of numbers or sets of numbers in the real number line, okay? So there's some notation involved with this. So interval notation, what we're going to basically do is we are going to go ahead and talk about a set of numbers as, you know, a list, right? So a list of tell me where the list begins, tell me where it starts, and then tell me where the list ends. So we typically write it in this way. We want to write down our starting number and then the number that we end with. And then we're just going to use either a parenthesis or a square bracket to indicate whether or not we are including those start values or those end values, okay? So here in a parenthesis is going to mean that we are not including that value in what we wish to talk about. So if you ever see a parenthesis in your interval notation, it means that we are not including that number itself. We're just going to include everything that comes either before or after it, okay? When you translate this to inequality notation, that's going to translate to either a less than or a greater than symbol without the or equal to part. That is for when we want to include the number, which is what we use a square bracket for. So this is what we use to indicate that we do want to include that value. And so we're going to have less than or equal to or greater than or equal to. But again, it always goes in this fashion right here. We always want to go ahead and list out what we are starting with and what we are ending with. And we are going to do that in order from smallest to largest here. So a couple of different examples here. We're going to just kind of convert between inequality notation and interval notation. Here, this inequality notation says x is greater than 4. So if I were to write out a verbal description for that, what we want to convey is this idea of all numbers that are greater than 4. Okay? So all numbers that are greater than 4. So you could think of some examples that would fit that description, right? So numbers like 5, 6, 7, etc. These are all numbers that are greater than 4. How would we write that with interval notation? Well, this description right here, I could look at as a list of numbers. Maybe a list that starts off with the number 4 since I'm trying to compare to the number 4. So that might be my starting number. And then I'll write a comma and then say, what am I trying to end with? Well, if you think about it, there are infinitely many numbers that are greater than 4. So this is going to go all the way out to positive a billion, positive a trillion, etc., etc., etc. These are all numbers that are greater than 4. So what we would say here in the interval notation is that for my ending number, I'm just going to go ahead and say that this list ends at positive infinity because it keeps going and going and going and never ends, okay? Now, let's go ahead and talk about whether we're going to use a square bracket or a parenthesis on this 4 and the infinity, okay? The idea is that you want to kind of think about this. Does 4 match this description? Does 4 itself match this description that says all numbers that are greater than 4? Well, I don't think it does. 4 is not greater than itself, so we do not want to include that 4. So I'm going to go ahead and put an open parenthesis around that 4 because we're not trying to include it. And then this is just a general thing. It says this up top here, but if you ever have infinity or negative infinity, you will always put a parenthesis around that. So we are never going to include infinity because of the simple fact that we will never reach infinity, okay? So that would be the way to write that using interval notation in that way, okay? So you want to kind of think about what the inequality says as an idea, and then you want to translate that over to your interval notation here, okay? So the next one, you might want to write a verbal description for this and just say x, which represents all numbers. That's how you would read that in the inequality notation. X is just all numbers. Well, all numbers that what? We'll just take this part by part, right? What does this say? This part of it says negative 2 is less than or equal to x, and x represents all numbers. So we want all the numbers that are going to be greater than or equal to negative 2, but also fitting another description, right? So this description right here, we also want all of those numbers at the same time to be less than 5, but also less than 5, okay? So how could we possibly convey that in our interval notation? Well, this is a little bit easier than the previous example because in terms of our starting and our ending number, they pretty much give that to us straight away here. This description is going to start off talking about the number negative 2. It's going to end up talking about the number 5. So when we write that, we're going to say that our starting number is negative 2, comma, our ending number is 5. All right? And now the simple matter of whether or not we are going to use a parenthesis or a square bracket. Remember that we use a parenthesis when we don't want to include that value, right? So we use a square bracket when we do. So if we look at this idea right here, this whole business of being greater than or equal to negative 2, the or equal to part, that allows us to go ahead and put a square bracket around that negative 2 because we wish to include it. But the thing about the other description is that we want these to be strictly less than 5, and 5 itself is not included in that description. So we are going to go ahead and put an open parenthesis around that 5 there. Okay, so a couple of nice, easy ways to think about how to translate from one way of saying this idea to another, inequality notation to interval notation. That's the basic idea there, okay? So I'm going to go ahead and move right along and talk about some more examples here. So it says, write the following in interval notation. So it's going to give us a verbal description for a couple, and then it's going to give us an inequality for a couple. I would encourage you to maybe pause the video and see if you can come up with a few of these answers here. And then once you are done, maybe unpause the video and see if you can give these a shot and see if you got them right. Okay, so I'm going to go ahead and work out a couple of these examples here. Hopefully you've had a chance to pause the video and give these a shot on your own, but we're just going to kind of blaze through these. So we are looking in the first example, real numbers that are more than 12. Well, anytime they talk about real numbers or all numbers, that is what we're going to let be x, and then the more than 12 part, that is what we're going to represent with either an inequality if we're being asked to do inequality notation, or here they're asking us for interval, right? So we're not going to introduce the x there. What we want instead is we want to compare numbers to 12. So we're going to go ahead and let that be our starting number. And then if we want all the numbers that are more than 12, well, there's infinitely many more than 12. So we're going to say that 12 is where we start, and then we end at positive infinity, okay? Are we going to do a parenthesis around 12 or a square bracket? Well, it's a matter of if we're including 12. And 12 is not going to fit this description itself. So we are not going to include the number 12 in this description. So we're going to put a parenthesis around that. And then remember that we always put an open parenthesis around infinity. So that would be a way to do that first one. Okay? For this next one, it says all non-positive numbers. Okay, so notice here that it does not say negative. So if you think about what's not positive, of course, the negative numbers fall into that category, but also there's one more that falls into that category, and it's 0. Okay, if you think about your number line, okay, all of the numbers to the left of 0, these are all your negatives. All the ones to the right are positives. but it just said non-negative down here. So what that's going to mean for us is that we want all the numbers that are in this range right here. So that actually does include 0. So when I write this, I'm going to go ahead and write it from least to greatest order. I'm going to say that my list starts all the way out here at negative infinity, and then I'm going to go all the way until I reach to my upper bound, which here is just going to be 0. Okay? Parenthesis around that infinity because we'll never reach it. And we do wish to include 0 here because that is a non-positive number. And so we'll go ahead and put a square bracket around that 0. Okay, so the verbal descriptions you'll have to think about a little bit extra, but still not too bad. These inequality notation ones, what you should have gotten for this one is going to be the following, and I'm not going to dive too deep as to why. If you have additional questions over this, then feel free to ask me in class, but this would be your answer for that one. So some parentheses around the -1 and the 4, because again, I don't see the or equal to's on those inequality symbols. For number 4, it says 5 is less than or equal to x. So to just be clear here, we're starting off with the number 5, and we want everything that's greater than that. Another way to write this would be to say x is greater than or equal to 5, where the inequality symbol opens up to the x, just like it did in the previous one. So I might start my list off here with 5, and then just say, because of the or equal to, I do wish to include it. And then there are infinitely many numbers that are greater than 5, so I'm going to go ahead and say it goes all the way to positive infinity. So there would be a way to write that using interval notation. And then the last one, just a simple verbal description here, just says at least 4. How do you even convey that, right? Well, if I'm at least 4, then that means that I am 4, or I'm something more than 4, right? Like if I'm 5, if I've got 5 apples in a basket, then I have at least 4 apples in that basket, right? So that means that I want to convey this idea of being equal to 4, but at the same time, I could also be greater than 4. So that would be at least 4 there. And to write that using interval notation, I would start my description off with the number 4, and then there are infinitely many numbers that are greater than 4. So I'm going to say from 4 to positive infinity, I am going to go ahead and include that 4, and I'll never reach infinity, so open parenthesis around that. Okay? So there's just some quick review over how to translate from verbal descriptions and inequalities to interval notation. That'll be something that I want you guys to work on and eventually have under your belts. Okay? Next example here, write the following in inequality notation. So here we're going the other way around. Here we're starting off with interval notation here in example number 6. We have to write that using our inequality notation. Okay? So it says all x in the interval from 4 to 19. Not including 4, but yes, including 19. Okay, so I'm going to go ahead and start this off by writing x. Our inequality notation always starts with that. And what I want to convey here is all the numbers that are between these values here, right? So I'm going to go ahead and say less than, and then 4 and 19, all right? And then a matter of including what is meant by these grouping symbols here, right? So the parenthesis means that I do not include 4, so for that reason, I am not going to include the or equal to part of that inequality. I'm just going to leave that as strictly less than. But for this other one, because I see a square bracket on that 19, that means that I am including 19, so I'm going to go ahead and write or equal to on that 19 there. And that will be the way that we can convey that, that set of numbers, but using inequality notation. And the next one, number 7, it says x is at least -3. Okay, so you got to think about what at least means, and this works exactly the same way as number 5 did, where we said at least 4. That means either I am equal to 4 or I'm more than 4. Okay, so if I were to write this in inequality notation, that would be to say that this number x that they want us to talk about, that can either be equal to -3, or it could be greater than -3. If I am at least a number, then I'm either that number or I'm something more than that number. Okay, so really straightforward way to go ahead and apply those. And then the last topic that we're going to discuss here in this notes is this topic of absolute value, and then we'll talk about some of the properties and do some examples as far as that's concerned. So absolute value basically just means that we are taking a number and we are finding its distance away from 0 on the number line, right? So for example, if I just write a preliminary example here, let's say I wanted to interpret the absolute value of 3. What is that equal to? Okay, well, if I think about the number line, I know where 0 lives. And what I'm doing when I'm doing absolute value is I'm calculating a distance. I'm figuring out how far away the number 3 is from 0. And that, of course, is 1, 2, 3 steps. So for that reason, we would simply say that the absolute value of 3 is equal to 3 because we did 3 steps to get to 0. And that's what an absolute value means. It's basically just a distance. A lot of people think of absolute value as just the thing that makes your numbers positive, and while that is true, we want to kind of think more about this distance context so that we can go ahead and always make sure that we are interpreting things correctly. So a couple of really easy examples here. Absolute value of negative 10. How far is negative 10 away from 0? Well, it's going to be 10 steps away from 0. So the absolute value of negative 10 is going to be positive 10. Okay? Some operations with some absolute values. So maybe we find the absolute values here first and then simplify. So the absolute value of 2, how far is 2 away from 0? Well, of course, that's going to be 2 steps away from 0. How far is 5 away from 0? Well, that, of course, is 5 steps away from 0. And then after that, we want to just subtract the 2. So 2 minus 5 is going to give us negative 3. Okay, so I wanted to include this example because sometimes, even though your problem deals with absolute values, you're going to end up with a negative result. Here in the next one, number 10, it says the absolute value of negative 1 over negative 1. Well, the absolute value of negative 1, that's just how many steps negative 1 is away from 0, and that's just one single step. Okay, and so really this turns into just that one step over negative 1, and 1 divided by negative 1 is just negative 1 itself. Okay, so again, the takeaway here is that even if you see those absolute value bars in your expression, your result is not automatically always going to be positive. You have to think about absolute value in terms of distance and then do the operations that you see here. Okay, I'm going to let you think about number 11 here. Okay, so this says that we have this expression that we want to simplify, and playing the role of x in this expression are going to be all numbers that are less than negative 1. Okay, so I'm going to let you think about how you might simplify that, and then if there's time at the end of the video, we're going to come back and take a look at what that conclusion should be. Okay, so let me go ahead and see if OneNote will cooperate here with me. Here we go. Okay, so properties of absolute value, right? So if we're talking about distance, what are some natural consequences of what we're talking about here? Well, first one says something really straightforward. Since absolute value is just distance away from 0, then that means the absolute value of any number you want to talk about is either going to be 0 steps away or it's going to be more than 0 steps away. That's what that first property talks about. Okay. This next one talks about distances as well. It talks about how if you've got a number line and you've got 0 there, if you've got negative a and positive a, it talks about how those distances are equal to each other. It's the same distance to get from negative a to 0 as it is to get to positive a from 0. So that's just talking about how those two distances are exactly equal to each other. This next one here talks about what happens when you take the absolute value of a product, and it says that you are always going to be allowed to break up the absolute values if the operation between these two guys is a multiplication. Okay, and then similarly for division over here, it's where we run into addition or subtraction with absolute value where we're going to have to be a little bit more careful. But multiplication and division, very nice and simply done. Okay, so let's take a look at a couple of examples there as far as that's concerned, and then we'll take a look. Okay, so it says the distance between 2 points A and B on a number line is basically just going to be the difference of those two numbers, but then the absolute value of that. Okay, so this notation right here is maybe some new notation for you. It's D parentheses A, B, all right? And so what that means is D stands for distance. Maybe make a note of that here, okay? So D stands for distance, and if you see that written on the page, they're just asking you straight up for the distance between the number A and the number B, okay? So that's what that stands for. That's just a little bit of shorthand notation so that we don't have to write out that whole mess. And here, playing the role of A is 2.3, and playing the role of B is negative 1.7. So if we're trying to figure out how far apart these two numbers are on the number line, you could draw it, but that would require that you actually draw a precise picture enough to count and get the right answer. Instead, we're going to go ahead and just use this straightforward formula up here. What we're going to do is find the difference of these two numbers, and then after that, take the absolute value of that difference, and that's going to be the distance between these two numbers on the number line. Okay? So we can pick the order. Apparently, we can go either B minus A, or we could go A minus B. That part is up to us. Let's take a look at what those two situations would look like. So if we did B minus A, then that would be, playing the role of B was a negative 1.7, and then we take away A, that was 2.3. What if we did the other order around? What if we did A minus B? Well, then that would look like this. It would look like your 2.3 minus your B, which is negative 1.7. And then, of course, we're taking the absolute value of whatever we get here and calling that our result. Okay? Well, here's the thing. It's basically up to you which one of these you would rather do. In that second example, I have a negative, that's a double negative, and we all know that that turns into a positive, of course, so you can go ahead and rewrite that as 2.3 plus 1.7, the absolute value thereof. Whereas on the top, you would have to kind of think about a negative minus another number. That's something you could easily do in the calculator, so it's not like you can't do it. It's just a matter of personal preference, okay? But we'll go ahead and just skip straight to the punchline on this because we're trying to call it a video here pretty soon. What you're going to end up here with in both cases is going to be 4. Okay, so the absolute value of positive 4 in the second example, and then the absolute value of negative 4 in this other example. And again, the distance that 4 is away from 0 on the number line is just going to be 4 steps in each one of these cases. So we get a result here of 4 no matter which way we do it. Okay, so the distance between those two numbers on the number line is going to be 4 steps away from each other. So here's just some refresher problems here. These are just going to be really quickly. Basically, we're evaluating expressions, right? So this doesn't necessarily have to do a lot with the stuff that we talked about previously in this video, but it does have everything to do with stuff that we're going to continue to do in the course, which is evaluate functions and doing that sort of thing. So it looks like my writing went away. Where'd happened to that? Oh, there it is. Okay. So let's take a look, right? When you evaluate expressions, you're basically just going to take the expression that you were given, and you are going to plug in the value that you were given. Okay, so playing the role of x here in part A is simply just the number 2. So that means that everywhere I see an x in my expression, I'm going to take it out, and I'm going to replace it with the number 2. So let's go ahead and do that. So we're going to have 14 minus 3 times x, but playing the role of x here is 2. We all know that 3 times 2 is going to give us 6, and we know that 14 minus 6 is going to give us 8. So to evaluate that first expression at that value, x is equal to 3, or sorry, x is equal to 2, I should say, we're going to get an output of 8. Very similarly done if our input here is now negative 1. We're going to have 14 minus 3 times that x value, negative 1. Plug that in. Careful here because we have a negative 3 times a negative 1. That's going to end up being a positive 3, so this will be 14 plus 3, and that will end up being 17 for you. Okay, so if you plug in a different value for x, you're going to expect to get a different output. Okay, and now for this next one, right? So just to be kind of clear here, anywhere you see one of these x's, that's where you want to think about there being an open set of parentheses for you to plug in. So what I might do here to make this a little bit simpler is for us to go ahead and replace each x that we see with an open set of parentheses so that when we go to plug in, it's going to be nice and easy for us, okay? So let's go ahead and copy that over here. So negative open parentheses squared plus 2 times open parentheses minus 3, and then same thing on part B. Negative open parentheses squared plus 2 times open parentheses minus 3. Cool. Okay, so now we're going to go ahead and plug in our answers, or not our answers, but our numbers for x. So here it's going to be 0 in this first case. So we're going to plug in 0 there. And then in this next example here, we have negative 2. So we're going to plug in negative 2 over here. Okay, so in that first expression, we just plugged in 0, and basically a lot of these terms are going to fall to 0 here. This is going to fall to 0, this is going to fall to 0, and then we have that minus 3 there. So basically we have 0 plus 0 minus 3, and that's just going to end up being negative 3 for us. Okay, so when we evaluate at x is equal to 0, we're going to get negative 3 in that case. Over here, we plugged in a negative 2, and here we're just going to have to remember our signs, right? So here we have a negative 2 squared, and that, of course, is going to make 4. But then we had an extra copy of a negative sign in front of that, so we'll call that negative 4, all right? The next little term there, that's us handling the first guy. Let's handle the second guy. That's a positive 2 times a negative 2. That's going to make a negative 4, and then we have the minus 3 there at the very end. Okay, so we have negative 4, minus 3. A little bit of mental math there. You're going to get negative 11. Okay, so evaluating expressions at certain values of x, very, very important. And again, that's just a little bit of a refresher from stuff you've learned in previous algebra courses. So that's going to do it for this video. I hope it's been of some help to you. So basically, you guys are converting between interval notation and inequality notation and verbal descriptions. You're dealing with absolute value, families of numbers, and evaluating expressions. So if you guys need some extra help, please feel free to let me know. But I'm going to call it a video. Thank you very much, and I will speak to you in the next one.